Okay, final hour of Physics 1C for November 24th. We're going to now be talking about what are called sinusoidal electromagnetic waves. This is one solution to the wave equation that we just derived. Sinusoidal electromagnetic waves. So these waves are going to look something like this picture down here to the left. This is your classic picture that you're going to see in basically any physics textbook that you pick up. Or if you were to Google electromagnetic wave, this would be one of the first pictures that showed up on Google. It's a wave that's oscillating in the y direction for the electric field component, and then it's oscillating in the z direction for the magnetic field component. These fields are always at right angles to each other here and here. And it's always the case that if you look at E cross B, it will give you the direction of propagation of the wave, regardless of if the electric field is positive or negative. And as we said before, the ratio of these fields is always going to be equal to the speed of light. All right. So they oscillate in phase as well, so that when the electric field is at a maximum, the magnetic field is as well. This is kind of required so that they can satisfy this equation. At any point in time, the electric field needs to be equal to the magnetic field multiplied by the speed of light. Okay, this always has to be true for these waves, which means that whatever the value of the electric field is and whatever the value of the magnetic field is, they have a constant ratio. If they have a constant ratio, then, when the electric field's at maximum, the magnetic field has to be maximum. When the electric field gets really small, the magnetic field has to get small, and so on and so forth. Ash says, so there are electromagnetic waves that are not sinusoidal. I'd say, yeah, for sure. And this type of wave that we're drawing right here, this would be, specifically, this type of wave would be a linearly polarized wave. And I'll say what that means in a second, but I'm just going to write the language down. So polarization refers to the direction that the electric field is oscillating. So if it's only oscillating along like this, I don't know if you can see the pointer there, so I'll just do it with the mouse. So if it's only oscillating like this, so it's just oscillating up and down along the y direction, then that electric field, basically, if you were to be looking at it as it comes towards you, it would just look like a straight line that goes up and down and up and down and up and down, right? That's what we call a linearly polarized wave. Anyway, but you could imagine that you could have a wave that could have a combination of a lot of different electric fields. After all, if I look at a point in space and I've got multiple electric fields at that point in space, then it's the vector sum of the electric fields that produce the total electric field at that location. And so you could have a wave that was composed of like multiple waves, where some of the waves are oscillating like this, and some of the waves are oscillating along the z direction. Some of the waves are oscillating at like a 45-degree angle in between them, and so on and so forth. And if you get enough of these added together, so that when you're looking at it, the wave right here, if you were looking at it, it would just be oscillating up and down and up and down and up and down like this as it comes towards you, right? If you combine with that a wave that's oscillating left and right, and then a wave that's oscillating at an angle, like this and this, and this and this, and this and this, eventually what you're going to do is you're going to form what's called circular polarization. I think I'm getting this right. Man, this sounds like it might be wrong, actually. Those of you that have taken 1D, does that sound right to you? That this is circular polarization? It does, okay. Good. Circular polarization, we'll just use that as a... so it's a combination of a bunch of these things, and I think generally... That's all I'm going to say about that. You'll learn more about polarization in your Physics 1D class, but for now, one thing to remember is that when they talk about that polarization, they're describing the electric field. And I'm sure that'll be mentioned when you get to it, too. Okay. So, let's talk about waves on strings really quickly. So, for a wave on a string, okay, what do I mean by that? Imagine that we have a string, and let's say that it's clamped at one end. If I oscillate the other end up and down like this, then I can produce waves that are going to travel like this on the string. And those waves, we could say they travel like in the x direction, and we could call this the y direction here. We could say that this could be defined as the amplitude of the wave. And for a wave on a string, you could have y of x and t be equal to something like this. Kx minus omega t, where the y coordinate is given like this. These parameters that show up inside of here are k. This is what's called the wave number. It's equal to 2 pi divided by the wavelength. This is called the wave number. K. You can't read that. I need to be... Wave number is k. 2 pi over lambda. And omega is something that you're kind of familiar with probably. It's 2 pi multiplied by the frequency. Okay, this is just the angular speed of the wave. And then the actual velocity of the wave, velocity, is equal to omega divided by k. It's also equal to f times lambda. And you should be able to prove pretty easily here that if you put f times lambda into here, you'll get omega over to k. Will we be discussing the imaginary component of this course? No, I don't think so. I don't think so. Okay, so that's a wave on a string, a cosine omega t. So a represents the amplitude of the wave, and then k and omega represent like the wavelength and the frequency, basically. For an EM wave, it'll look a little bit different. What we're going to have is our electric field, the y component of our electric field as a function of x and t, is going to be equal to the max value that the electric field gains, so E max, multiplied by also like a cosine function, cosine of kx minus omega t. That's just the y component, which implies basically that the electric field at any moment in time is just equal to that value, EY, multiplied by J hat. And we could use that if we want to describe the electric field as a function of time. Sorry, I didn't mean to draw it out like that. Where if you wanted to write it as a vector, you'd write it as E as a function of x and t is equal to J hat times E max as the cosine of kx minus omega t. We can do the same thing for the magnetic fields. The magnetic field we would write as Bz of x and t is going to be equal to B max multiplied by, they have to be in phase with each other, so this also has to be cosine of kx minus omega t, because they have to be in phase. And then the actual magnetic field, the vector magnetic field, would just be equal to k hat multiplied by B max, and then multiplied by cosine of kx minus omega t. So that would be an example of what the magnetic field and the electric field would look like as they oscillate in time. And according to what we said earlier, the direction that the wave propagates is given by, they say it up here as well, is given by E cross B. So in our case, if we do E cross B in this case, E is J hat, right? And K hat. So if we do J hat cross K hat, what's that equal to? If you remember, this is I hat, right? You can use the right-hand rule to prove that as well. The J cross K is equal to I hat. So that's the direction of propagation. So that's the direction that it's moving. And in accordance with what we wrote here, at any point in time, if you ever need to know, if you're only given one of these and you need to find the other one, you can always use this relationship that E max is equal to C multiplied by B max. That's kind of a helpful thing to know. So if you only knew one of the equations, you could get the other equation by knowing this here. All right. Now, if I wanted to produce, this would be, so direction is positive I hat, right? So this is positive x direction. That's the direction the wave's traveling, right? If I wanted to produce a wave that travels in the negative x direction, I can change it just a little bit. Does the word traveling have two L's in it? It looks wrong. I guess it doesn't matter. Yeah, it's one L, huh? Okay, I guess I should fix that. All right. So for a wave that's traveling in the negative x direction, then you just need to have one of these change a little bit here. So one example of that would be like if I have E of x and t, and I have my magnetic or my electric field be the same as it was before. Maybe y'all can tell me. What should the magnetic field be then? If I want it to move in the negative x direction. That's exactly right. Just make it negative k. Because then, if I do E cross B, I'm going to be doing J cross negative K. And that's equal to negative I hat. So that would be negative x direction. And so on and so forth. You could figure out what do I need to do to make it travel in the positive z direction or the negative z direction and so on and so forth. You just need to alter what component you're talking about here, right? All right. So let's do a problem. Kind of apply what we just learned. All right, so carbon dioxide laser emits a sinusoidal electromagnetic wave that travels in vacuum in the negative x direction. The wavelength is 10.6 micrometers. And the electric field is parallel to the z-axis, so we're changing things a little bit here, but they've drawn a nice picture for this. So the electric field's now in the z direction. The magnetic field's well, it doesn't tell us, but our goal is to write the vector equations for E and B as a function of time and position. So we're really only given lambda, and we're given Emax. This is all that we're given. And we need to basically fill out our equations. So Emax is 1.5 megavolts per meter. And we need to write down equations for the electric and the magnetic fields. Okay. Knowing that it's traveling in the negative x direction, okay, means that if the electric field is parallel to the z-axis, the magnetic field is going to have to be parallel to the y-axis. In order to make it travel in the negative z direction, to make it travel in the negative x direction, we can kind of acknowledge that if I do k hat cross j hat, that gives me negative I hat. So that's why this picture below will work just fine for what we want to do. All right, let's start off by writing down the electric field equation. Our electric field equation, as a function of x and t, we said above, is equal to E max multiplied by the cosine of kx minus omega t. And in this case, it's going to be multiplied by k hat to make it point along the z direction only. So we just need to be able to figure out what k, omega, and E max are. So let's go ahead and start doing that. First of all, how can I figure out what k is? It's the wave number, and what is it equal to? 2 pi over lambda, exactly. So that's easy enough. So k is going to be equal to 2 pi divided by our wavelength, lambda. Can you all calculate what that is for me? What's k equal to? 6 million. Anyone else get the same thing? Yeah, okay. So it's 6 times 10 to the 6th. The units for K, they're going to be inverse meters, but usually the way this is written in textbooks is radians per meter. Okay. It's kind of like radians per second, but it's radians per meter. Has to be that way because if you think about it, you're taking the cosine of something, you're multiplying by x, so it kind of needs to be... Oh, so Ty got a different answer. You rounded aggressively. Very clearly. Well, no, his is different too because it says 10 to the 5. He's saying it's 10 to the 5. The denominator is 10 to the negative 5, basically. And you're doing 6 over that. Yeah. Should be 10 to the negative 5. Okay. Yeah, let's... Alright. So, 5.93... I think it's okay to just do 5.9 times 10 to the 5th. Thanks for correcting that. I appreciate that. All right, that's K. All right, what else do we need to find? We need to figure out what omega is. How can we figure that out? If we already know what K is, what equation can we use to figure out what omega is? I'll scroll back up. The velocity of the wave is given by omega divided by k. We have k. Yeah, so just c times k, right? So if c is equal to the angular frequency divided by k, that tells us that c times k is going to be equal to omega. So c is the speed of light. Got to remember this when you're doing these problems. It should show up in basically all of them. Multiplied by k, which we just found. So we'll write it as 5.93 now, times 10 to the 5th. If I write it as radians per meter, then we'll get our answer in radians per second. (1.78 times 10 to the 14). Y'all agree? Now we can actually write down the electric field as a function of time. So E as a function of x and t is going to be equal to, so it's k hat times E max, which was 1.5 megavolts per meter, multiplied by the cosine of kx, so k is and then minus omega, which is 1.78 times 10 to the 14 radians per second, times t. So that's E as a function of x and t. Our goal was to find that as well as the magnetic field as a function of time. How can I find what do I need to do for the magnetic field? We know the magnetic field's also going to be cosine kx minus omega t, and then as Ash is saying, we can apply the fact that the magnetic field should be equal to, so B max should be equal to E max divided by the speed of light. So we just take that, 1.5 megavolts, so that's times 10 to the 6th volts per meter, and we divide by the speed of light, so by 3 times 10 to the 8 meters per second. And that's going to give us our magnetic field. And I think you're going to get something like 5 times 10 to the negative 3 Teslas. Yeah, That's going to be B max. And then we just put it all together. So B of x and t is going to be equal to j hat, because we want k cross j, times 5 times 10 to the negative 3 Tesla, times cosine of, and then all this junk, 5.93 times 10 to the 5th radians per meter times x minus 1.78 times 10 to the 14. Man, what am I doing tonight? I'm just getting ahead of myself as I'm writing. 10 to the 14 radians per second times t. And there we go. That's our magnetic field. Anyone have any questions? Pretty easy. I mean, I don't know if it's easy, but simple kind of algebra. Okay. The next thing that your book talks about is how electromagnetic waves work in matter. And you're welcome to read that if you want, but it's something that if you've taken 1D, you've probably talked about. It's something that you're going to talk about in 1D anyway, but the point is that these coefficients that show up, the epsilon naught and mu naught, can be shown to produce something that's called the index of refraction. I'm going to leave that for you guys to read yourself, though, if you want to, just so that we can get on to the next part to help you solve some of the problems that show up on your homework. Okay, so electromagnetic waves carry energy, and they carry momentum as well. And so we'd like to be able to describe what kind of energy they carry. And in order to do that, we're going to use something that's called the Poynting vector. But to start, we're gonna remind you. So we're going to derive what the Poynting vector is and how we calculate it. That's the goal of this section. And really, what this is going to be, it's going to be a way to describe the intensity of a beam of light. So ideally, after we discuss all of this, you'd be able to describe how you calculate the intensity of a beam of light. All right. Now, to get started, we're going to go back to something that we derived. I feel like this was last week. So if I have an electromagnetic wave, it's going to be composed of energy densities associated with the electric fields plus the magnetic field energy density. Okay, this is what we're writing down here is going to be energy density. Energy density, which basically just means energy over volume, right? Just like normal densities are. We derived back in the chapter on capacitors that the energy that's stored inside of a capacitor is given by this expression, 1/2 epsilon naught multiplied by the electric field squared. And then in the chapter on solenoids, once we learned about the energy that's stored inside of an inductor, 1/2 Li squared, we proved that if you plug in the inductance of a solenoid and you replace the electric field, the current with the magnetic field that produces, that you can say that for the magnetic field, you get 1/2, or really 1/2 mu naught, multiplied by the magnetic field squared. That was the energy per unit volume that you would have in something that has an electric field to the magnetic field, and this would be the energy per unit volume that would be carried by an electromagnetic wave. However, since we now know that there's a fixed ratio between the magnetic field and the electric field, we can actually simplify this quite a bit. We know that, let's just do this in a different color. We know that the magnetic field is equal to the electric field divided by the speed of light. In addition, we also know that the speed of light, I'll write this up here because I think we're going to use it quite a bit, is equal to 1 / the square root of mu naught times epsilon naught, right? So B equal to E over C, another way you could write it is the electric field multiplied by the square root of mu naught multiplied by epsilon naught. Right? So if C is equal to 1 / that, then 1 / C is equal to this, right? So if I take that B that's equal to this and I plug it into that equation, let's see what we get. So now what we're going to get is the energy density. The first term is going to remain unchanged, so we have epsilon naught times E squared. But for the second term, we're going to get 1 over 2 mu naught multiplied by b squared. But b squared is now going to be e times the square root of mu naught epsilon naught. We square that whole thing, and then what we get, with a little bit of algebra, the mu naughts cancel, and it turns out to be the case that you get 1/2 epsilon naught e squared here, and you get the same thing here. So if you think about it, what this means is that man, my hand is really cramping up here, writing in the way that I am, so I need to stop for a second and just stretch my fingers. What you end up getting here is that these two, right, they're equal to each other. It's kind of surprising. I don't know if it's surprising, but what it means is that the energy that's carried by these electromagnetic waves is equally carried between the electric and magnetic fields. That's kind of... It turns out that this quantity, the energy density of the electric field, is exactly equal to the quantity of the energy density. These are equal to each other, actually. That's kind of surprising, I think, at least. But nonetheless, that means we have a really simple expression for the energy density now. Now the energy density is just equal to this plus this, which 1/2 plus 1/2 is 1. So it's just epsilon naught times e squared. That's a really simple equation, right? Really simple equation. All right, so we're going to start with this, and we're going to use it to derive the intensity or the energy carried by these waves. We know the energy density, we know how fast they move, so we can describe how quickly they carry their energy. Now for this, we're going to want to use this picture. Again, this is a picture that I could draw myself, and like maybe it would help you, but their picture is just really good, so I want to use their picture. All right. So that we're just going to start from there. That's the energy density of an electromagnetic wave. Look, it's proportional to the electric field squared, right? So let's take our plain electromagnetic wave, and let's put it down here. So the same kind of picture of our wave that we've had in the past. The idea is that it's a plane wave, and we're looking at a single wavefront at a time dt after it passes through the stationary plane with area A. So here's one plane, and we're looking at our wave as it passes through that area of space, basically. And we're just looking at one piece of the wavefront. After all, this is a plane wave, so it goes up and down infinitely and left and right infinitely, basically. And yeah. Okay, so this is the wavefront at some time dt later. And what we're going to do is we're going to use this equation that they've written right here. And we're going to say that the volume between the stationary plane and the wavefront is going to contain an amount of electromagnetic energy that's going to be equal to this. And why is it equal to this? Well, we know that the energy density is U. And energy density is energy per unit volume. So if I multiply this times volume, right, then I'm going to get the amount of energy that's contained within this region of space here. And we're going to call that D, and I'm going to use the symbol to be a capital U. Okay, so big U is going to represent just energy itself. Not energy density, just energy. The energy of the wave, so to speak. And we're looking at the energy that's contained basically within this little region right here. How much energy is in that volume? And we already know that the energy density is little u, given by this expression right here, so epsilon naught times e squared. But the volume is going to be the area multiplied by the distance. This distance right here, we could call it x, but in this case, it's equal to c times dt. And the reason it's equal to that is because the rate at which the wave moves is the velocity of light, and we're looking at where it is at a time dt later, right? So if I take area and I multiply by that distance that it's traveled, c dt, then I'm going to get the amount of energy that's contained there. Right? All right. It's the energy that passes through A in the time dt. So, what we're going to do, because we're interested in a kind of intensity here, we're going to say let the symbol S, okay, be equal to the rate of change of the energy, kind of the rate at which the energy is flowing, dividing the dt to the left-hand side. I'm also going to multiply this times 1 over the area, and that is equal to epsilon naught times e squared, and then what's left over here is this c. right? So why did I do it this way? Well, the amount of energy du that passes across this distance in a time dt represents basically power. And I'm dividing that by area. So the power would be the rate at which energy is being transmitted, basically. And we're dividing by area here because what we're interested in is the symbol S. But what I'm going to say now is that if I take, in physics, if you take power per area, the units on this are watts per meter squared. I don't know if that helps you. What is power divided by area in physics? Has anyone seen that any other place in physics show up? Yeah, it's intensity, exactly. This is what we call the intensity. If you have an object that has really high power and really low area, it's going to produce a really intense amount of energy. All right? A good example of this is if you stand right next to a speaker at a rock concert, it's going to produce a really intense sound. I did not spell intensity right. I don't know what's going on with my writing today. It's just awful. Intensity. You stand really close to a speaker, then all of the power from that speaker is focused in a really tiny area, and it's extremely loud, right? And you get farther away from it, though, that power is distributed over a wider area, and the intensity is smaller. A laser beam, light bulbs, when you buy them, are measured in power, watts, so they're not necessarily measured in intensity. However, this is relative to a light bulb, too, because if you get really close to a light bulb, the power is spread out over a smaller area. Let me explain it like this. If I have a source that's producing power, like a speaker that's sending out energy, then when you get a certain distance away from it, it has to spread that energy out over all of this area right here, right? And if you go farther away, it has to spread that energy out over a bigger area. The energy comes out in, like, basically spherical kind of things. And the intensity is inversely proportional to how far away you are. The farther away you are, the more that the power has to be spread out. Lumens is a different measure. Okay, so lumens actually might be a measurement of intensity. Maybe you can look that up, but I can't remember. I think lumens might be. Candela. You think about candela? Mr. Meowers? Yeah, candela is, it's a unit of, I think it's a unit of stellar brightness, right? Oh, I always forget if it's a unit of intensity or if it's a unit of brightness. I think it's a unit of brightness because intensity is, look, intensity has units of watts per meter squared, so it's a derived unit, right? The candela, is it the SI unit of intensity? Okay, now I'm interested. So why do we need it then? Because it's it auto-corrected to candelabra. Okay. It says luminous intensity. I think this is a little bit different because it's luminous intensity. I think it's not the same thing as watts per meter squared. Let's see. It's definitely not the same thing as... Oh, here we go. A 25 watt compact fluorescent light bulb puts out around 1700 lumens. If that light is radiated equally in all directions, i.e. over 4 pi steradians, which is, this is a three-dimensional version of a radian, it'll have an intensity of lumens per steradian. And that's the candela. So lumens and candela are very much the same thing, because radians aren't really a unit. Okay, so this is intensity in terms of, it is a different unit, basically. definitely a different unit. Monochromatic. Where did it say that? Well, this one it's saying it's in equally in all directions, though. Focused into a 20-degree beam, the same light bulb would have an intensity of around 18,000 candelas. So it's going to depend on like how intensely the brightness is. Yeah. No, it's not one direction, Ash. It's a steradian is it's the three-dimensional version of a radian. It's like a cone. Does that make it three-dimensional? It's like a cone. And then, so this is the easiest way to think of a steradian. So a steradian is what's a radian? A radian is related to circumference, right? Where there's 2 pi radians in one circle. And yeah, how many steradians are in a sphere? Be 4 pi. Because the radian is a measurement of length. It's a ratio of lengths, whereas the steradian is a ratio of areas. It's a ratio of areas. How much? See, think about it like this: a steradian is a ratio of how much of the total surface area of a sphere is given by this portion of it, basically. Whereas a radian is how much of a portion of the arc length is there relative to the total circumference, right? All right, so yeah. Okay, so steradian is another way to define intensity. But we can also define intensity in terms of power per unit area. You've never heard of this before in your life? So the candela, it's interesting. I think it comes up in astronomy. I think I can safely say, without ever having taken an astronomy course, like, I've taken astronomy courses, but not like, I haven't taken modern astronomy courses, that candelas may show up in astronomy. But, oh, why hasn't steradian come up in physics? I don't know. We haven't needed it, I guess. I don't know. It didn't really come up very much in my physics studies either, but I mean, it did come up, at some point. It just... Okay, so intensity is power per unit area, right? And our goal here is to figure out what's the intensity of a light wave. Well, according to what we just said right here, it's equal to epsilon naught times the electric field squared, and then times c. But what we'd like to do now is we'd like to get our magnetic field back into this equation. So we're going to want to use the same relationship we used up here, which is that our electric field is equal to the magnetic field times the speed of light. But now we want to basically replace one of our electric fields here. So let's do that. We'll say this is going to be equal to epsilon naught times c, and then we're going to have electric fields. But then we're going to multiply this times the magnetic field. And the magnetic field is equal to c times b. So we multiply this times c times the magnetic field. And we end up getting epsilon naught times c squared e times b. But this is usually written in a simpler form because epsilon naught multiplied by c squared, what's that equal to? Well, c squared is 1 over mu naught epsilon naught. So if I multiply both sides by epsilon naught, then epsilon naught times c squared is going to be equal to 1 over mu naught. And we can plug that in here. So we end up getting that this thing S, which represents the intensity of our wave, is equal to the electric fields multiplied by the magnetic fields and then divided by mu naught. And this thing is what we call the Poynting vector, okay? But it needs to be a vector form before we can truly call it the Poynting vector. So the vector version of this... My God, what am I doing with my writing today? There. As a vector, we're going to define the Poynting vector to be S, put a little arrow on top, and it's going to be E cross B. Now, this gives us the Poynting vector at a moment in time. This is kind of the instantaneous Poynting vector. Because we know that the electric and magnetic fields are oscillating in time. So if we want to find the average Poynting vector, it's going to be half of this. And I'll derive that as well. And we do this because the frequency of these waves is so extremely high that the average value tends to be what's more relevant. Man, do I need to go through this derivation? We've done the same derivation so many times about how to average cosine functions and sine functions. I don't know. We can do it, I guess. I don't know how useful it is. I'd almost rather do a problem, but anyway. So that's the Poynting vector. I'm just going to tell you what it is. You can go look up the derivation if you want to. It is super easy to do. I'll describe how you do it. The average value of the Poynting vector is going to be equal to the maximum value of the electric fields multiplied by the maximum value of the magnetic fields and then divided by 2 mu naught. It's basically just divided by 2, but you replace E. This would be the actual definition of the Poynting vector is E cross B, but the average value you can prove pretty easily is E max B max divided by 2 mu naught. This is going to be the one we want to use more often than not. And why do we use the average? We use the average because the frequencies that we're talking about here are on the order of 10 to the 14 hertz if we're talking about light. And that frequency is so insanely quick that you can't really notice the fluctuations that are coming. This is something similar to a question that was asked when we were talking about AC circuits, which was that when you're looking at the light that's coming from a light bulb, I've got a light on in my room right now, I look at the light bulb, and it looks like that light is producing constant light. Last time we talked about that in terms of the way in which the current was flowing within the light bulb, but now we can say, well, that light bulb is producing a light wave, and that light wave is coming to my eyes, and the frequency at which it's oscillating up and down is super fast. I can't possibly draw 10 to the 14 hertz per second anyway. It isn't 10 to the 14 hertz, I mean, because it's just it's going from max to min to max to min to max to min so frequently. And the reality is, I don't even care about the minimum. It doesn't get negative. There's no negative light intensity. It's always going to be positive because you're multiplying this times this, and it's related to E squared, right? So we don't really worry about the instantaneous Poynting vector when describing the energy that's coming from a light beam. So the Poynting vector is always parallel to the direction of propagation then. Yeah. It has to be, because this is... Okay, so what is the Poynting vector? The Poynting vector is intensity, which means the power that's coming out per unit area. So whatever direction the light's coming towards you, that has to be the direction of the Poynting vector, right? Because the Poynting vector is just the rate at which energy is coming to you, right? It's the rate at which energy is coming to you divided by the area. So it has to point in the same direction as the propagation. That's right. Anyway, you can prove for yourself that you get this by taking the value for the electric field that we got in the last problem. You know, the E max times the cosine of kx minus omega t, and then the B max times cosine of kx minus omega t. You do some, vector additions, or some cosine function stuff. And anyway, we've actually done the exact same thing before. Do we want to do a problem real quick before we stop? I don't think we're going to get to momentum tonight. I think we'll have to do that next time. But we will. We will get to the momentum. Okay. Well, let me put it this way. If you've got power per unit area, if you're delivering energy to a surface, right? Let's say you take a laser beam, right, and you shine it on a mirror, and it bounces off the mirror. If it's sending energy into the mirror, it must also be transporting momentum too, right? Are we talking about momentum of the photons? We can describe it without actually talking about photons at all. But yeah, it's basically the momentum of the photons, yes. Yeah. It's like the pressure the photons create when they hit a surface. Yeah. Let's see if we can do a problem real quick before we stop. We can probably do 2 problems, actually. So I just want to emphasize, by the way, that I remember learning about the Poynting vector as an undergraduate and then learning about it in grad school, and it always felt like this really ephemeral thing to me. It's just a really fancy name for the intensity of the light. That's all it is, right? But it specifically refers to the power per unit area, or kind of the rate at which energy is coming to you. Okay? All right. We can do both these problems. They're pretty short. Okay, energy in a non-sinusoidal wave. For the non-sinusoidal wave described in 32.2, we didn't do that part. It's a very silly section, but you can read it if you want to. Suppose that the electric field is 100 volts per meter. Find the value of the magnetic field, find the energy density, and find the rate of energy flow per unit area. S, the Poynting vector, right? Okay, so if I've got an electric field that is 100 volts per meter, I can find the magnetic fields by taking the electric fields and dividing by the speed of light. So that would be 100 volts per meter divided by 3 times 10 to the 8 meters per second. 10 to the 2, 10 to the 8. It's like 10 to the negative 6. 1/3 of that. It's like 0.3. Something like 3.3 times 10 to the negative 5, maybe? Could someone verify that? I probably got that wrong, right? Ooh, I have the answers in front of me because I actually worked on this. No, it's 10 to the negative 7 because I'm bad at math. It goes the other way, not the way I went. It was negative 6, so it needs to get smaller. This is negative 7, and then you get Tesla. You can prove for yourself that volts per meter divided by meters per second gives you Teslas. It does, for sure. Second, find the energy density U. Okay, that's easy to do. The energy density is epsilon naught times E squared. So it's 8.85 times 10 to the negative 12. What is this? Okay, so Newton meter squared. Coulomb must be Coulomb over Newton meter squared, right? I think that's what that unit is. And you multiply by the electric field squared, so times 100. Let's write this as newtons per coulomb whole squared. Does this work out? Let's see. Coulomb squareds cancel. One of the newtons cancel. You end up getting energy density, which ends up being newtons per meter squared, which is right, because that would be like newton meters per volume. Yeah. 100 squared is 1e4. I think that's right. That one I got right. And then finally, we want to find the flow per unit area S. So the rate of energy flow. So that doesn't say average, right? It just says the rate, right? So we'll say then that S magnitude is equal to E times B divided by mu naught. So that's going to be equal to E, which was 100 volts per meter, times B, which is 3.3 times 10 to the minus 7 Tesla, divided by mu naught, which is 4 pi times 10 to the minus 7 Tesla meter per amp. Okay, don't fault me too much if that's wrong. I think that's what it is. We'll see, Teslas cancel. 1 over meters and meters. Those cancel. Volts divided by... I'm starting to think maybe this is not quite right. Tesla meter per amp. I got to think about this. B is equal to mu naught times I over 2 pi r is the magnetic field of a ring, so it would be Tesla times mu... Oh, it is. That's right. Okay. Not immediately clear to me how these units work out here. Yeah, 26.4. That's right. Unit should be watts per meter squared. Oh yeah, meter, you get meter squared, and then the amp times a volt gives you watts, because amps times volts gives you watts. Yeah, that works out fine. This would be like the maximum value, though. That's like the maximum. You could call this S max if you want to, I believe. Oh, this one isn't even oscillating, though. I think if you go, it's non-sinusoidal. Okay, I don't. Oh, is it 26.3? Actually, I wrote on my notes that it's 26.5, so I guess it depends. It probably depends. It's like 26. Let's call it 26. All right. I actually don't think we have time to do the other one, but we can do it next time. So next time, what we'll do, and this will be a week from now, since we don't have class because it's Thanksgiving, we're going to talk about the last section here, which is the momentum flow and radiation pressure. We'll talk about solar sails. I'll see if I can't find a video about solar sails. that we can watch, and then from there we're going to talk about the Maxwell's equations in differential form. So I'm going to write down, I got to find it real quick just to show you. If you want to prepare for next time, if you're interested in looking at it before we get to class, what you'd want to do is to look at Appendix C in the Physics 1 C Lab Manual. Let me just make sure that's correct. Yeah. So Physics 1 C Lab Manual, Appendix C. If you're interested in kind of being prepared for next time, if you want to be able to follow along and understand what we're doing, you'd want to kind of read from the Physics 1C manual, Appendix C. Okay. Oh wait, so it's going to be 12-1. What is it next? What is next time? Yeah, 12/1. That's our next class. Oh my god. Okay. It's like 7 or 8 pages, maybe 10. But yeah. Nathan, next Monday is fine. You can turn that one in. Really, you can turn it in just next week. Is fine. Next week's fine on that one. For the lab manual.